Well, welcome to your first video lesson on atomic structure during this COVID-19 outbreak. You'll notice I'm wearing this mask, which I will now take off. But before I talk about what the mask is for, I'll let you know that Mr. Coffin, Mr. Ford, and I are going to team teach the physical science the rest of the way. You'll still have your individual teachers, but we're going to kind of combine efforts. Right? So there's a little controversy about these masks because what do? Do they actually stop the viruses? Well, first of all, viruses are really, really small. Right? So head of a pin actually figured out about 33,333 viruses can fit across the head of that pin. All right, so I think, okay, well, popcorn kernels are pretty small, right? So what I did, I took some popcorn kernels and put them on some double back tape. There's about 100 there. Okay, my goal was to get 33,333 across there, but I stopped after 100. If I had kept going, it would have been about 180 meters. For those of you who slept through the metric system, that's about 2 football fields. So 2 football fields of popcorn kernels. If you take that popcorn kernel, condense it to the size of a virus, you get that right across the head of a pin. All right. So why talk about? Well, viruses are made up of. Okay, we're getting ahead of ourselves a little bit, but I got to do it. Here we go. 4 major elements: CHON, PS. You guys can figure out what those are. Okay, see if you can do it. You know the symbols already. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. All right. Okay, these 4 right here. Okay, here's your trivia for today. Those are the 4 most abundant elements in the universe. Those are the 4 most abundant elements in our world, and they're the 4 most abundant elements in your body. So what does that tell you? Think about it a little bit. All right. So those viruses are really small, but what makes up a virus are actually atoms, and that's what the lesson is about today. Okay, so atoms are really, really, really small. Okay, so first of all, let's start with this. Okay, an element. Okay, what is an element? Okay, there's periodic table. I'll show it right here. Okay, you probably won't be able to distinguish it, but periodic table of elements. There's 92 natural elements. Okay, with man-made, it's around 110. You can ask Mr. Ford; he'll probably know exactly. Okay, but those elements are made up of atoms. Okay? Okay. So what is an atom? Okay. Atom is the smallest part of that element. All right. Okay. So if you take an element, copper, okay, or iron. Let's take this copper right here, for example. You take this copper, which is there's trillions and trillions of atoms in there. If you cut it in half, cut it in half, cut it in half, kept doing that, you would get down to 1 atom eventually. Okay? That's the smallest part of that atom which retains those properties. If you cut it smaller than that, then you get to subatomic particles. Okay? So for those of you taking notes, and there might be a note sheet in your folder, okay? An element there, okay, is made up of 1 atom type. Okay, and we use symbols to simplify things. So, for example, we just had carbon up there. Okay, so carbon, we just use C. Okay, so the element carbon just has carbon atoms. Okay. We take copper. Copper is Cc, so it's Cu. It's just made up of copper atoms. Okay, so we use those symbols to kind of simplify things. Okay, an atom, okay, is the smallest part of the element retaining the properties of that element. So a lot of times you use those terms interchangeably, but just know that's the relationship. Atom, smallest part of that element. Okay, element just made up of that, all that 1 atom type. All right. So atoms are really small. Okay, so to look at them, we need to use models. Okay, so you're familiar with a lot of atoms. If I asked you to draw an atom, you would probably do something like this. Let's say I asked you to make let's say an oxygen atom. You would put, I do this, you probably put a little dot in the middle, and then you may put these rings around it like that. And that is a really good model. Sometimes that's called the solar system model, where you have an ultra-dense nucleus, and then you have these electrons which orbit around in these distinct orbitals. Okay, that's a good working model, okay, but more accurate is the model which is now called the electron cloud model, where you have an ultra-dense nucleus, but around that you have these clouds of electrons which exist in what are called energy levels. Right? So we use different models to help us because atoms are so small. Okay? They're so small you can't see them, right? So we make up these models, okay, which show the characteristics. All right? So back here, if I'm making a carbon atom here, okay, most of you put the electrons on the outside here, okay, and we'll come back to that in a little bit. All right. Now, atoms. Atoms are the smallest part of an atom which retain those properties, but the atoms themselves are made up of even smaller particles. Okay, there's three major subatomic particles, okay, which I've listed in a little table right here. Let's just go ahead and fill that out. Most of you are familiar with this, and again, we're team teaching this, so we're kind of coming together. So for some of you, some classes we're a little further ahead, so maybe backtracking for some classes may be right appropriate for others. But let's go through this. Protons, and we use the symbol with a little P plus. That's what I use for protons. Okay, so it tells you P, it's proton plus, gives you plus charge. Its location is in the nucleus. Its mass is 1 AMU, that's atomic mass unit, and its charge is, of course, plus. Right? Neutrons, oops, not N, we'll just use a little N for that. Okay, again, it's in the nucleus. Okay, it's got a mass of about 1 AMU also, and its charge is no charge. So I'll put a 0 there. It does not have a charge. And then electrons, we use a little E minus. That gives something away on the charge, of course. And it exists in the cloud or energy level around the nucleus. In its mass, it's got a mass, but it's essentially 0. Okay? It's actually about 1,840 times less than an atomic mass unit. But for figuring out mass for atoms, we don't even worry. It's too small. Of course, the charge is a minus. All right. So those are called subatomic particles. Protons and neutrons are actually made up of particles smaller than those, but we'll get into that when we get into the nucleus, study the nucleus. All right. So I got cut off there. I was trying to do a single take, but it's okay. So let's finish this off. Atomic structure. Okay. Some definitions. Atomic number. Okay, that's the most definitive thing about an atom. That is just equal to the number of protons. Simple. Okay, an atom is what it is because of the number of protons. An atom can have a different number of electrons or neutrons. Okay, but if a different number of protons, that changes what it is. Okay, mass number of protons plus neutrons. All right, those are things in an atom which have mass. Protons and neutrons. Add those up. Okay. Isotopes. Okay, isotopes it's going to be same number of protons, different number of neutrons. All right. So here's what it gets. You take an atom like carbon. Okay, this is how they write it many times. Carbon 12 would look like this. That would be the mass number. And this would be the atomic number. Right? So carbon can exist like that, and if it exists like that, we can tell how many protons it has, how many neutrons it has, and how many electrons it has just by looking at those numbers. The atomic number is down here. That's the number of protons, so that would be 6. Okay? Mass number here, okay? Mass number, remember, is protons plus neutrons, okay? So if you have 12 for the mass number, atomic number 6, okay? It would also be 6, okay? 6 plus 6 is 12, okay? Electrons, if it is neutral, it's going to be 6. You have the same number of protons as electrons. They balance each other out. Right? Now, carbon can also exist like this, though. 6 and 14. Right? So in that case, it's going to have, that atom would actually have 6 protons. Okay? 14 minus 6 is 8, so it would have 8 neutrons, and electrons would be 6. So they're the same atom, they react the same, they just have a little bit different mass. Those are called isotopes of each other. Okay, so same number of protons, different number of neutrons. So that means same atomic number, but it would differ in its mass number. Now, in nature, you have both those existing. Actually, some atoms have more than 2 isotopes. Okay, but it's the combination, the average of that in nature, which gives its atomic mass. So if you look up carbon in the periodic table for mass, it will say, for carbon, it's going to say 12.011. Okay, that's its AMU. All right? Okay, so what does that mean? That means that it exists in more than one state, okay? But there's a lot more of the carbon-12 than of the carbon-14 because the average is much closer to 12 than it is to 14. All right? So the atomic mass is equal to, okay, that's the average mass of all the isotopes, that particular atom. All right? All right, so the final concept is concept of ions. Ions are simply charged atoms. Okay, so that means they got either a plus charge or a minus charge. Okay, so charged atoms. So let's take oxygen for example. Oxygen, if we draw the electron configuration of it, I'll put a nucleus there. Okay, and I'll put a couple rings around it. Okay. So for oxygen it looks like this, 8, 16, that's one of the isotopes. So that means it's got, how many protons? It's got 8 protons. 16 minus 8, it's got 8 neutrons. And it's got 8 electrons to start with. Okay? But now here's one of the golden rules in chemistry. Every atom wants its outer shell filled up with electrons. Okay? So let's put in the electrons here. Turns out 2 can fit in the first shell. Okay, the first row of the periodic table will tell you that. The second row can fill in to 8. So it is a lot of times called the Octet Rule because there wants 8 electrons in the outer shell. That will fill it up. Okay, so for oxygen, it can either gain 2 or lose 6. Okay, so law of least effort, it's going to be much easier for it to just gain 2 electrons somehow versus trying to lose 6. All right? So what it does, it gains 2. Gains 2 electrons, so that means it now has 8 protons, and it's got 10 electrons. All right? So you can see it's got a mismatch here, more electrons than protons. So what you do is, how many more electrons than protons? Well, it's got 2 extra electrons, so we say that gives it a 2 minus charge. Okay, so then you signify that, you have oxygen symbol, and then they write that as a, I call that a superscript. All right, so oxygen generally has a 2 minus charge. Okay, something like chlorine, okay, which has 7 electrons in its outer shell, will gain 1, so it's got a 1 minus charge. Something like sodium, okay, which has 1 extra electron in its outer shell, it's going to tend to lose that electron, so you would get a 1 plus charge. All right. So I know the structure, the sheet we gave you has some of those problems on it, so that's how you work with the ions. Okay, so the sheet you have, you should be, with this information, you should be able to fill it out. Okay, atomic number, mass number. One last thing, the atomic mass though, you will have to use a periodic table for that, so you can access that on your own, or we'll try to put one in your folder. Alright, so I hope this first lesson is beneficial for you. Again, review for a lot of you, but some of you, get you back in the learning mode. Alright, see you next time.